Okay, so I wanted to finish up the real Fourier analysis on the real line with a couple of things. So, which is one is the thing that I was saying, another approach to L2 theory. The reason I introduced, not that we will use it, but it's nice to know that there are these approaches and there is this whole business of Hermite functions which come in. Okay, so what did I do? Here I defined, you started with the Gaussian. Phi of x is e to the minus x square by 2 divided by square root of 2 pi. Then we know that its Fourier transform is square root 2 pi times 5. No means I just asserted it. If anybody is unfamiliar with this, I will be happy to explain the proof either privately or in lecture. But it's also a good exercise to try and prove it. It's there in lots of books, of course. So then phi hat is that. Then we have this, I just out of nowhere, I brought this operator A, which is minus of the derivative plus multiplication by x. Okay, so this is the operator A. So you keep applying this. So the point is, if you apply, so what we have already understood what happens to, if you know the Fourier transform of f, what is the Fourier transform of the derivative and what is the Fourier transform of x times the function. Okay, so basically x time function, its Fourier transform is the derivative of the Fourier transform, and derivative of f, its Fourier transform is lambda times the Fourier transform. So these signs are chosen properly. There are factors of I and so on, so one should be careful. But you can check, we check this, that if you take minus d dx plus x times f, then g hat of lambda turns out to be minus I times the same operator applied to f hat. What I mean here is that it is same as I times, is it minus I or minus I times A applied to f hat. Okay, or g hat is I time minus I times A f hat. So because of that, so that's a nice relation to know. If you combine the derivative and the multiplication like this, then you get something that is preserved more or less except multiplication by a constant. So if you multiply on the, so rather let me write it like this. AF hat is minus I times A applied to F hat. So this A commutes with the Fourier transform. Basically what we are saying is this is commuting with the Fourier transform. Almost there is this factor of minus I. We understand precisely how it commutes. That's the point. I mean, what is the factor is minus I. Okay. So because of that, if you keep applying it to phi, A phi hat is minus I times A phi hat, but A phi, so but phi hat is multiple of phi. So square root 2 pi times A phi. So you get that originally phi was a Fourier, was an eigenvalue of the Fourier transform with eigenfunction of the Fourier transform with eigenvalue square root 2 pi. I am using eigenvalue, eigenfunction just in a purely formal sense. If you want to make precise those things, you have to bring the spectral theory and other things, which we don't need to. Here, I'm not even going to use that. So we'll just take it like this. So we call it, it looks like if you apply this Fourier transform to phi, you get square root 2 pi times phi. So we'll call this an eigenfunction with eigenvalue square root 2 pi. Then A applied to phi also will give an eigenvalue, but with minus I square root 2 pi. And if you apply one more time, you will get minus I square and so on. So A to the P times phi is an eigenfunction of the Fourier transform with eigenvalue minus I raised to the power pi P times square root 2 pi. Okay, what are these functions going to look like? So let's compute maybe one or two of them. Then you will see what they look like. So phi of x is 1 by root 2 pi e to the minus. Actually, since I'm talking about eigenfunctions, that 1 by root 2 pi is not necessary, but for me it's always safer to keep it so that I don't make mistakes. So this is this. So what happens to it under, so A phi? means you have to take minus phi dash of x plus x times phi of x. Okay, what is that? If you differentiate this, so 1 by square root 2 pi will come out, and if you differentiate a exponential, you will also get e to the minus x square by 2. That is always going to remain even if you differentiate. So I can pull that out, and what I am left with is, when I differentiate phi dash, I'll get a minus x down, and there is a negative, so I get x. And then plus x times phi of x. So, oh, did I make a mistake? No, it is correct. So it is 2x times phi of x. So apply one more time. Just this is the last computation I will do. Just if we do that, we'll have to differentiate this. Okay. So we'll get minus 2 phi of x minus 2x phi dash of x plus we'll have to multiply this by x. So that will give 2x square phi of x. Now we know that phi dash of x is already phi dash of x is x times phi of x, right? Or minus x. Is it phi dash of x is minus x times phi of x. So I can again pull out a phi of x out. What I'm left with is minus 2. And then here I think I get plus 2x square. Another plus 2x square. So you get 5x into 4x square minus 2. Okay. So it is easy to see just by the structure of this that a to the p phi of x will look like phi of x times some hp of x, where hp is a degree p polynomial. It's a degree p polynomial. So these are called Hermite polynomials. There are different normalizations, but there are different normalizations. So some books may have it differently, but this is okay. You can call this Hermite polynomials. So these are the functions which look like this. Okay, so this a to the p phi are phi of x times. This is exactly of degree p. Okay, and something you see various properties one can see. One can write explicit formula, which is not useful, but other things are useful about it. But one point is that because of this, we get 1 point. Okay, so what I want to say is that so any polynomial can be written as a finite linear combination of hp times phi. Because if p is some polynomial of some, I mean, this p is not to be confused with hk phi. Okay, k equal to 0 means okay, a to the power 0 phi is just phi. That is also part of our a to the 1, a to the 2, and so on. You can compute a few. You can compute all actually explicitly. But any polynomial times phi of x, any polynomial, well, you can write it in terms of these polynomials, right? Because these are exactly degree p. So first you try to take the largest power and use the corresponding Hermite polynomial to cancel that off. Then you get a lower degree polynomial and you so on. It is easy to see that. Therefore, so these are in the span of these things. So the claim is that this is actually, so let me leave it maybe as exercise. Is dense in L2 of R. So every L2 function can be approximated by these polynomials times Gaussian. Okay. Therefore, what we have is
Quick question.
yeah.
Why do we write it as, why not just say any px can be a finite linear combination of hp of x?
True. But here, yeah, you are completely right. So here in this statement, I could have just erased this phi on both sides. Yeah, completely
Okay.
correct. There, except that when I talk about L2 of R, I will always have the factor of phi x. Polynomials are not in L2 of R. After multiplying by the Gaussian, they are going to be in L2 of R.
I see. Thanks.
Yeah. So this is dense. Okay, actually, let me see if it is easy or not. Maybe it is not that easy. But let's take this for a fact now. Okay, so these are dense in L2 of R. Now what we see is that the span, so hence span closure of these things, hk of x, phi of x, k greater than equal to 0 is actually L2 of R. Because all these are in the span, so the closed span is that is same as saying dense in this. But now what I want to say further is in fact hkx phi x is an orthogonal basis. It's not orthonormal. You have to find normalization constants which can be found. It's an orthogonal basis.
Sorry, Manju, have you started recording the lecture?
Oh, have I not? Okay, I thought. Yeah, I have. I have.
Okay.
Thanks. Though, I mean, yeah, I tend to forget. Thanks for reminding. Yeah, so I have started, it seems. So this hk of x phi x is an orthogonal basis for L2 of R. So it's one of my complaints about this all these courses that we teach in math is often we talk about L2 spaces and so on. But after a full functional analysis course, many people will not be able to give a concrete basis for L2 of R. You know that it exists, but that's about it. So if that was by chance your state of knowledge, then now you know an explicit basis. You can get many bases. One simple way is, yeah, there are many bases you can get, but this is a very important basis which occurs quite a lot. Okay, so this is an orthogonal basis for L2 of R and also eigenfunctions of this operator. Okay, so this is the nice thing about it. So why is it orthogonal? Let's prove that.
Just to understand that statement, if I replace HP with something like Bernstein polynomials or something like that, the statement will not be true, correct?
No, there will be a basis is okay. Span closure, this part will be okay. If you take even hk to be just simplest would be x power k.
Exactly, yeah.
So if you take x power k phi of x, yes, the span closure is exactly this, the span is exactly this span and that will be dense. But they will not be orthogonal.
Okay.
Phi of x and yeah.
I see. And okay, so just like that, Bernstein may or may not be orthogonal. Okay.
No, it will not be. If
okay,
you want it, if you want it against phi of x,
I see.
then you have to, I mean, there's no other choice actually in some way, because what you get is, I mean, not that there's no choice. If you take phi of x times 1, phi of x times x square, phi of x times x, phi of x times x square, dot, 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 and apply Gram-Schmidt to this. What you get is exactly phi h1 times phi, h2 times phi, and so on. Okay, this is another way I could have introduced it. Then I would have to argue that that is how A acts on it. I defined it, these things to be A applied to A to the power k applied to phi. But you could also have defined like, well, anyway, you have to make a link between the two. So from what I'm going to say, it will follow that this is what you will get if you apply Gram-Schmidt. Okay. So that's the fact. Gram-Schmidt means where there are options in Gram-Schmidt whether you normalize or don't normalize. Here it is not normalized. Okay.
Great, thank you.
So that is what it is. Yeah. So you won't get anything else if you want degree 1. So you can do it in some other way. You can put this in a different order, then you will get a different thing. But if you put it in the order 1x x square, which is the most natural, then the Gram-Schmidt is the only way. I mean, the only orthonormal basis you will get by Gram-Schmidt is this. So there won't be anything else that works. So if you, yeah, so that's the point. Anyway, so now let me prove orthogonality of these things. So why are they orthogonal? So let's look at hk of x, phi of x, hl of x. Everything is real valued, by the way. You notice that I don't need to put conjugates here because everything is that's what it is. Okay. So if you do this, how do we see orthogonality? Okay. So yeah, what should I do? 1 second. Let me see. Yeah, maybe I write it in the original form. A to the k phi of x okay. So what is A? A is x, and here let us assume k is larger than L without loss of generality. So let's take k bigger than L. So why would this be true? So to see that, what we do is we integrate by parts. You transfer. So suppose I want to integrate by parts, but A is not just derivative, it is derivative plus x. So let us make a small observation. If I have A times f of x into g of x dx, what happens to that? That is minus f dash of x plus x f of x into g of x dx, which is the first integral is minus f dash g. Everything is vanishing at infinity and so on. So when you do that, you will get f g dash with a negative goes away. Okay, and the second one will be just x f g, x f of x g of x. Okay, so this is actually, so in other words, this is integral of f against a star g, where a star g is d by dx plus x. See, the negative goes away because of integration by parts. So I have derivative of g plus x times g. So I write it like this, f into, I take f as a common factor and write it as d by dx g of x plus x times g of x. So this is actually the adjoint of that other operator. In the, when you make all the setting clear, that will be how it will work. So the point is we will, yeah, but now I don't see if I can get the answer. Actually, this won't work. I think I may get into trouble.
But maybe Manju, you can just the original integral. Why don't you take the use Plancherel and Fourier trans? Take the integral is same as the integrals of the Fourier transforms, right?
That is true.
But then constants will, they are eigenfunctions, so the constants will come out, and then it will be the same, right?
Oh, I see. Okay, that's a clever way. Okay, that's a very clever way. So what I was trying to do, let me just say, I thought that, let me just, so Kaushik's suggestion is probably the better one. So let's just, let me just, since I have written this much, let me just say that a to the L phi of x dx. I think this will be, is this 0 is a question, because I think, see, a to the L phi of x, yeah, that won't be exactly 0. Actually, its integral against phi will be 0. So that's the problem. So point is that L is a, I mean, if it was simply a polynomial, okay, if it was not phi of x, but a to the L phi is some polynomial times Gaussian, and now you will differentiate more times than the degree. So it should become 0. That was the idea, but I think this is not exactly 0. So let me just leave it. Maybe there is this should be a way to continue here, but instead let me take Kaushik's suggestion. That's a nice one. So if you take HK phi inner product HL phi in L2, this is same as their Fourier transforms. So, but I mean, but whether it will give always for k not equal to L is what slightly I'm worried about. So it is HK phi hat HL phi hat. Okay, actually, what is the Plancherel say? I have to see that. What is the factor between? Oh, actually, sorry. I mean, so yeah, what is the? Okay, but Kaushik, let me not do this. Let me leave this as exercise. It will probably come out. But one point is, yeah. So the what I was trying to do, in a way, is an alternate approach to the L2 theory. So one approach I gave is via Plancherel. You prove Plancherel theorem for L1 intersection L2 functions and then use the density of L1 intersection L2. Okay, so here I'm trying to supposedly give an alternate approach to the L2 theory. So let me not assume that Plancherel theorem has been proved. I think that is the point. I mean, so it's tantamount to that. So somehow this is 0. Okay, let me leave this as exercise in the interest of time. Okay, so this is 0 somehow. So you will have to prove that. I will write maybe in the notes if I get time. So then this is how orthogonality comes. But once we do that, but you try the other way. Try also the way Kaushik said. If you assume Plancherel theorem in this form, f hat square is 2 pi times f square, then and the corresponding thing for inner products, f hat g hat inner product will be 2 pi times fg inner product. Then by applying that to HK phi, HL phi, you probably get that that's equal to some constant times itself, which then that constant is not 1. Then the quantity has to be 0. But anyway, assuming all this, so let's now have, so now given f in L2 of R, right, f has sum over k equals 1 to 0 to infinity. F inner product, let me give it a name. This, okay, whatever this, okay, maybe no need for a name. F inner product HK phi times HK phi. That is how the this is. And define F hat by linearity. We'll just put it through here, and HK phi hat we know is minus I to the power k HK phi, right? I may have mixed the minus I plus I. Let me see. Minus I to the k square root 2 pi. There's also a square root 2 pi. This. So we will define it as minus I to the power k square root 2 pi HK phi. This is also an L2 function. You see, if you define like this, the Fourier transform, then this is clearly an L2 function. Because what is the L2 norm squared? Is the sum of squares of coefficients. This is using the orthonormality of the orthogonal. You have to be careful about the norms of this. It will be sums of squares of this with taking into account the norms. Okay, if these are not normalized. But for f hat square, it will be same sum of squares of this with the corresponding norm squares. Right. So that's what I mean. So f hat L2 squared will be summation f HK phi, the coefficient squared, and then I get an extra factor of 2 pi times HK phi L2 norm squared. But that is also the same as 2 pi times F L2 square. So in fact, this is Plancherel formula. So this is Plancherel. So this is an alternate approach to L2 theory, but of course I have left out one thing. You should be careful that if F is in L1 intersection L2, we have two definitions. Are they the same or not? Okay. So one needs to check. One should check here to make this a definition. One must check that this definition agrees with the other one. If F is in L1 intersection L2. Because then you have two definitions, they agree. That's one has to check. Anyway, the reason I went into this is to just introduce Hermite functions, which are something that is worthwhile knowing. They occur in lots of places in mathematics. Okay, any questions, comments? Okay. So then let me go on to what is next. The one more thing that I wanted to do, Poisson summation. It is a useful formula with lots of applications. Okay, it's a kind of duality principle. So let F be an L1 of function. Okay. So the way what we will do is we will relate L1 functions. I mean with L1 functions on the on the circle. How we will try to periodify that. So define G. Okay, I will right away say this, but this will be clear afterwards. G of x. I mean, you know, L2 of t is we are writing as 0 to pi if you want. Okay, so this is 0 to pi. So how do I get g of x? So f is some function. Maybe like this. So 0 is here, 2 pi is here. What we will do is we want to make a periodic function using f. So we will just wrap it around. So if I take an x here, we will take all its periods. X plus 2 pi, x plus 4 pi, x plus 6 pi, and also x minus 2 pi, x minus 4 pi, and all that. So we'll define as the sum over n in integers f of x plus 2 pi n. Of course, this is an infinite sum. Does the sum converge? I mean, that's not immediate. So why does the sum converge? So note, if we do this and then integrate it over the torus with respect to x, that is same as, I mean, everything is positive. I put the absolute value inside, so you can do it in either direction. So this is 0 to 2 pi f of x plus 2 pi n with absolute value dx, which is same as 2 pi n to 2 pi n plus 1 of absolute value of f. Right, that is just the f of x plus 2 pi n that goes from 2 pi n to 2 pi n plus 1. So this is just the same as integral over r of mod f, which is the L1 norm of f. So that is assumed to be finite. What this says is that, so this function is integrable. So this is integrable on the torus. Hence, finite for almost every or for almost every x in the torus. Right? If you have a function of x which can be integrated, then it should be finite for, it can be infinity on a zero measure set. So in other words, thus the series defining G converges absolutely for almost every x in the torus. Torus here I'll write as 0 to pi. So it is a well-defined function, and in fact it's an L1 function. That's and in fact, and this also justifies G in L1 of t. With L1 norm of G is actually not same as L1 norm of F. It is bounded by the L1 norm of, well, I should put a 1 over 2 pi because for me on the torus the L1 norm is defined with 1 by 2 pi. Here I had not done that, so I can put 1 by 2 pi here. So, but it's an inequality because I put absolute values inside. So G is an L1 function. So the point is we can take Fourier coefficients. So f hat is a function from R to C. It is its Fourier transform. And G hat, despite possible ambiguity of notation, I will use this hat is Fourier transform for functions on R. This hat is Fourier transform for functions on T. So this is a function from integers to complex numbers, right? Because G is in L1 of T and T hat is integers. Here F is in L1 of R and R hat is R itself. So question is, how are G hat and F hat related? Okay, what is the relationship? That's what we are going to ask. So let's do a calculation somewhat formally. So if you do Fourier coefficient of some G hat of K, by definition, it is the integral 0 to 2 pi G of x e to the minus I k x dx over 2 pi. Okay. And what is G? G is a sum of these things. So it is now this is we can, so we know that this is anyway absolute value 1. So again with absolute values inside, this whole thing converges, so we can interchange integral and sum. If you put everywhere absolute values, then the whole thing is okay. That is what I computed here, right? So anyway, this has absolute value 1. So we can do it in the other way, and then we will get 0 to 2 pi f of x plus 2 pi n e to the minus I k x dx over 2 pi. Now what is that thing? So this integral is oh sorry, something is okay, no problem. So it is 2 pi f of sorry, so this x plus 2 pi n, let's call it y. So then y goes from not 0 to 2 pi, but 2 pi n to 2 pi plus 1, 2 pi n plus 1, as we did before. So y goes from 2 pi n to 2 pi into n plus 1. I have f of y, but I have e to the minus I k x, e to the minus I k x, e to the minus I 2 pi k n is equal to e to the minus I k y, but this is 1 because k times n is an integer. Everything is integer, so this is just e to the minus I k y dy over 2 pi. which if you just write it back again, this is just the integral over the real line f of y e to the minus I k y dy over 2 pi, which means it is the Fourier transform of f in the real line evaluated at the integer k divided by 2 pi. So the Fourier coefficients of g, which are defined only for k integers, so here k is an integer, is actually essentially up to a constant same as Fourier coefficient of f. F hat is defined for all real numbers, but only the integers come out. Okay, so that is what we get. So this part is completely correct. There is no problem. So now what? So this is the relationship. Then what? So now we will get the point. Get to the point. So now, so under some conditions, okay, so we will have to come up with what those conditions are. How do you write a function in terms of its Fourier coefficients? Right? So we want it x by x. So what is the condition? So not L2, but for each x. For each x, we want this. We haven't written a condition like that, but for a moment, let's assume that this is valid. Because let's not worry about that. We can write down some conditions. We can put strong conditions on G under which this convergence happens not only in L2 sense. I was always writing this in L2 sense. But if you put strong conditions on G, then it can also be true in pointwise sense for each x. So to say G is continuous is not enough. Maybe I'll come back a little bit to that. So what does that say? So G of x itself is a sum. This is saying that f of x plus 2 pi n is equal to sum over k in integers. Now g hat of k is f hat of k over 2 pi. E to the ikx. We get this kind of funny formula. Particularly, let's set x equal to 0. What you get is sum of the function values at 2 pi times integers is the same as the sum of the Fourier transform at integers. So there is a 2 pi factor here. Let me put it 2 pi here. So you get this. So basically you are summing function over, well, not integers exactly, but 2 pi times integers. So f is being summed over 0, 2 pi, 4 pi and all that, minus 2 pi and so on. And the Fourier transform is being summed over at integers. So they are the same. So that's the funny formula. Okay, this is the Poisson summation formula. Sometimes this is also called Poisson summation formula. And you can recover that from here. If you to remember, this second one is easier to, but you can apply it to a slightly different function and get that. This looks a bit more general. We specialize to x equal to 0, but here also this is true for all sorts of functions, right? We haven't exactly said what functions this is valid for, but you can change the function and quickly get this one for general x. That's not a problem. So either of them can be called Poisson summation formula. So this is a very interesting one. And sometimes also when you want to apply it, be careful about now the normalization of the Fourier transforms and so on, because one of the reasons why some people normalize differently is that in the Poisson summation formula, it can look a bit more symmetrical if you want. You can write it as the value of f evaluated at integers sum is equal to value of Fourier transform summed at integers. You don't have this, that one side you have 2 pi times integers, other times integers, but that's all not a big deal. It doesn't change any real content of anything. You just stick to one convention and don't make the mistake I did of trying to move to another convention. Then everything gets confusing. Okay, so this is, so when is it valid? That is a question. So we don't care about generality. So let's not care about, if we don't care about generality, yeah, is there a question?
Just a speculative question, like does this generalize in some other way, like for rationals or in other sort of not just integers but other nice
Groups.
things?
Yeah, so yeah, I mean, so I had mentioned Poisson summation formula in the discrete setting, if you remember. So you take a subgroup of Z mod n, for example, then there is a kind of, so let me show you. This is actually, so in the quotient and so Z mod n, basic properties, let me see here.
It's the right next one. You have written Poisson summation.
Okay. Thanks. Yeah. So here, the formula was written like this. I didn't give any serious applications of it. Yeah. So it was basically, no, not this. This was the motivation, but here, yeah. You have G and G hat. And what I had done was, where is the formula? So the function value summed at the elements of a subgroup is related to the Fourier transform summed at the characters of the quotient group. Okay. So in particular for Z mod n, it was function value summed at multiples of P and function Fourier transform values summed at multiples of Q. That's the thing. So this was the Poisson summation formula. In general, locally compact abelian case also, I think there is one. There is a notion of dual lattice and so on. So if on this side you get some subgroup and then that side you get some other thing. But okay, I'll have to think. I mean, I'll have to look up. But this is valid.
So there is some,
for RD, this is valid. I have not said anything. I have said everything in the real line, but everything goes to higher dimension. That's not a problem. Okay, and that's very useful. So I will remark on Rn, everything that we did is easily generalizable to higher dimension. Okay. Any other questions? Okay, if you don't care about generality, assume that F is in the Schwarz class. So remember, Schwarz class means if you take any number of derivatives and they multiply by any polynomial is bounded. So this is the definition of Schwarz class. Those are very nice. And so there it is actually quite easy to sum. So then, of course, these are, I mean, so this should exist. Okay, so F is, of course, smooth and so on. So F is C infinity, first of all. And this holds. So then it is kind of easy. I mean, because you see, then F of X is bounded by some constant over, let us say, X square. I mean, but you can put any power if you want, or X power 20 also. That's not a problem. Hence, for each X, the series converges rapidly. See, as you take X plus 2 pi n, that is, this term is bounded by something like 1 over n to the 20 or any power that you want. This decays faster than any polynomial as n goes to infinity or minus infinity. So this converges rapidly. And G is also a C infinity function. Okay, first of all, this would, from this rapid convergence, you will be able to show that G is a continuous function. If you use, you may remember uniform convergence and other things. So the sup norm of this, in fact, you can bound it by 1 by n to something. So this will converge. So Weierstrass M test tells you that G is a continuous function, but you can do it for derivatives of f also. And hence you can get that G is in fact smooth. I will leave this as exercise. In basic real analysis, there's nothing subtle about this. Or there's, you should treat it as a serious question and write an honest proof, but there's nothing complicated about it. So this is all very nice. It converges nicely, and also the Fourier transforms also converge. G is C infinity, and then and also f hat of t also decays rapidly. There is no problem. You can put to any power, and what is the thing that we needed? And g of x equal to g hat of k e to the I k x. This is valid for each x. Okay, because g hat decays so fast, these are all going to be 2. Okay, so I will just leave the checking to you if you want to check. It is very easy. So in other words, so for Schwarz-Class functions, so conclusion is for Schwarz-Class functions, it is fine. Okay, so that's a bit too much, you may think. Why I want to apply only to Schwarz-Class. Sometimes it's just easy to state theorems for Schwarz-Class, then you can generalize it. Okay, you can take approximation using Schwarz-Class functions and so on. But another reason I did it is, so I looked up, many places give Poisson summation formula without exact conditions. Okay, so I looked up one book. There is a book by Pinsky which I have referred to. There he says that Poisson summation formula is valid if we assume that f is in L1. So L1 is enough to get the almost sure convergence of G, right? For almost every x it converges. So f is in L1, and he assumes that this side is absolutely summable. Okay, so he says that is enough to ensure this. It seemed reasonable, but Katz-Nelson seems to explicitly say that this type of thing is false. Katz-Nelson's book. So, and he gives a counterexample in an exercise which I haven't gone through. So I want to be, so that seemed reasonable when I read Pinsky, because okay, when f is in L1, all this Fourier coefficient computation is okay. And the question comes whether this is valid pointwise. Now, if g hat k is summable, then is this valid? I mean, I don't know, but it might be true. I am not sure. Pinsky just says this. Then he says that, okay, once that is valid, then you can get this equality, x by x, and for x equal to 0, you get this. So, but Katz-Nelson seems to completely say that this is, even if both sides converge absolutely and f is, and f hat are continuous, he says is not true. So I am a bit, I want to just check that point. But for Schwarz-Class, there is no problem. Okay. Any questions, comments? So one example
sorry, if G is summable, like whatever that coefficients are summable, like in Pinsky's, then that surely that convergence is true, right? Because right hand side will be a summable thing and it will be a continuous function. And it almost and the Fourier coefficients match with G, so it has to be equal.
It has to be equal. That is what it seems, but I'm a little yeah, I don't know. Maybe I misunderstood the objection in Katz-Nelson, but Pinsky gives this as a theorem. Yeah, what you say is right. If the right hand side, if G, this we know in L2 sense. Okay, so this right partial sums converge to G in L2 sense. Fine. Now, if G hat is summable, then pointwise this converges, right? Because it converges absolutely. So pointwise limit has to be same as L2 limit. I mean, it converges even uniformly. So that uniform limit has to be same as L2 limit. So G has to be that. So then X by X we seem to get. So I don't know exactly what is the problem. I will check Katznelson's example. Maybe it is that. Yeah, okay, I don't know. As written, maybe this series doesn't converge for all X. That is possible still. But I'm not too sure. Let me see that example and then clarify this point.
Oh, you mean okay? So you mean that at zero maybe you may know it for all values, almost all values, but you may not know it for zero. Is that the point? Or
yeah, that's exactly what I surmise, but I'm not sure if that is the real point. Yeah, that's what I was saying, that for the particular X, whether this G of X is defined as this, but this may not be converging or something, or it may not be equal to that anyway. So
okay, I get it. Yeah, thanks.
So yeah, we are specializing to particular X, so that's the thing. But I think it should be easy if you at least put some smoothness assumption and decay. But okay, I'll have to see that. One example to which Poisson summation is applied is you take, let's take e to the minus x square over 2 sigma square over sigma root 2 pi probabilist normalization as the normal 0 sigma square density. Then we know f hat of lambda is actually e to the minus lambda square. I mean, I told you last time how it scales, e to the minus lambda square sigma square by 2. So when you, this one, when sigma is small, this one's, I mean, the variance is wide. Okay, so this is part of the uncertainty business I mentioned. So in fact, let me just take this opportunity to mention an interesting theorem called Hardy's theorem, which we will not prove, but one of the experts in that is Tangavelu in our department. He is an expert on uncertainty principles. In particular, he has Hardy's theorem in many situations. So it says that suppose f is an L2 of our function and fx is less than equal to e to the minus ax square by 2 times some constant. And but f hat also decays fast, like a Gaussian. Maybe a different constant times b lambda square by 2 for some c dash and b. So here it is a and b. So for example, for the Gaussian itself, a we can take to be 1 by sigma square and b is sigma square, right? That's how we have. So the claim is if ab is bigger than 1, then there is no such function. F is constant 0. And if ab is equal to 1, then f must be actually a Gaussian. Multiple of it, okay, essentially. So it's a constant multiple of that, okay. So it's a very, so this also is an uncertainty principle saying that, but this is capturing the decay in a different way, not by saying that a function is compactly supported or that other ways, but it is taking the how fast f decays at infinity as a measure by comparing it to a Gaussian. What's the Gaussian with which you can dominate? The larger the a, the faster f decays. But both f and f hat cannot decay too fast. Both a and b cannot be too large. Yeah, so I thought I'll mention anyway. So we are not going
Manju,
to.
maybe you can finish the if
Yeah.
a b less than 1, then there are then infinitely many such f.
Yeah. So I don't know what else is there actually. I mean, if a b less than 1, what should I say?
Then there are infinitely many such f which have which decay like that. For instance, this Hermite.
Hermit works. Yeah, Hermit works, but even Gaussians you can take it themselves. So that's why I didn't write, because you can slightly decrease the Gaussian, right? Then many such functions. I mean, what I mean is this itself, you have a leeway here, right? So you can take Gaussian, but with varying A. What I mean is, and B, with still the product being the same. But you are right. So one example linking to the ones that we were doing is, for example, hkx e to the minus x square by 2. Or ax square by, okay, minus ax square by 2. This kind of thing. Maybe, yeah, let's take a equal to 1. So basically Hermite polynomial times that will do. Maybe I should scale both sides. That's the reason. Hk of I should probably write hk of x root a times e to the minus x square a by 2. So it's the hkx e power minus x square by 2 that I had scaled by square root of a. So this, because these are not exactly satisfying this with a, right? I mean, so this is okay. So this is not the same a. It is actually for any a dash less than a. Because there is an extra polynomial factor. It's not bounded by constant times that Gaussian. So anyway, there are lots of examples. This part is saying that there is no such function. Okay, so let me just finish what was I planning to say? Poisson summation formula, how does it feature here? This is a rapidly decaying function in the Schwarz class, so everything is fine. So what we get is that Poisson summation, if you apply here, let's apply in this form, f of x plus 2 pi n, so will give me e to the minus.
It's 1 o'clock.
E to the minus lambda square. So I have to sum it over f hat of at k. K will give me k square sigma square by 2, and I have e to the ikx. Right. So in particular, when x is 0, you get yeah. So yeah, what did I want to say? There is nothing I wanted to say right now. So there is also a 2 pi factor here. So 2 pi is there. Yeah. So what did I want to say something here? Not really. The thing is, one side, the point is the one side sigma square occurs in the denominator of the exponent. In the other side, it is in the numerator. So if you take sigma large, this is rapidly converging. This is maybe somewhat slowly converging and so on. But anyway, there are applications of this. Maybe I will come to that. So this is related to what are called theta functions, and there are some duality relations there. And various functional equations like the zeta function, functional equation, etc., can be derived from this kind of Poisson summation formula. Okay, I will stop here. So I will just stop here.